will study phase shift in RC circuit in this lecture. Actually, we are studying voltage divided by BJT amplifiers for the last couple of lectures, and we have studied that the input circuit is such that the input AC applied input voltage sees capacitor C1 in series with the input impedance of the input resistance of the amplifier. The complete resistance or the equivalent resistance of the input resistance of the amplifier is called Rin, which includes R1, R2, and beta times Re. Right. So what happens to V base? The input voltage V base, as we have the C1 second R, so we'll apply voltage divider theorem. This is a recap from the last lecture. Rin over Re plus JXC1 times V A. So since this is a complex number, this one in the denominator, we can convert it to and it is in rectangular form, and we can convert it to both the form by computing its magnitude and writing it at an angle of this theta. And we know that the magnitude is computed as computing square root of the real parts squared plus the imaginary parts squared, and angle is inverse tangent of the imaginary part divided by the real part. We already know this from the complex numbers from circuit analysis. Right. So the phase shift introduced in Vn is at an angle of 0. So the voltage across R would be lagging, and it would be lagging at an angle, this inverse tangent of Xc1 over Rn. So it's a high pass circuit with this phase shift. Theta phase shift is inverse tangent of Xc1 over Rn. Right. So let's see what the numerical value of this theta is when we have F very large in midband. In midband for midband frequencies, F is very large. So F is very large for these midband frequencies. F is very large. So if F, if F is large, since Xc1 is inversely proportional to F, so if F is large, Xc1 has to be small. So if Xc is small, so if F is very large, Xc is very small, F tends to infinity, Xc1 tends to 0. So it's a very small resistance, very small impedance or capacitive reactance divided by Rn gives us a result very close to 0. So and we know that inverse tangent of 0 is a 0. So we have 0 degrees phase shift. That is amazing. That is superb. That is what we want. But what happens at FCL, the lower cutoff frequency, this one, at this frequency? What happens at this frequency, at the lower cutoff frequency? Of course, we know that from the last lecture, we know that at FCL, the lower cutoff frequency, Xc1 is Rn. So we'll replace Xc1. With Rn. So it becomes Rn over Rn. Inverse tangent of 1. Since tangent is sine over cosecant, and 1 means that it is the angle for which sine and cosecant they have the same value, and that is 45 degrees. And this means that at FCL, at this lower cutoff frequency, this input RC circuit formed by the input resistance of the amplifier and the externally connected capacitor C1, the coupling capacitor, the input coupling capacitor, the network formed by this RC circuit introduces a phase lag of 45 degrees at FCL. But what happens at FCL divided by 10? And we studied in the last lecture that if we divide FCL by 10, of course Xc becomes 10 times Rd. Why? Because Xc is equal to Rd at FCL, and if we divide FCL by 10, Xc is multiplied by 10 because they are inversely related. So theta becomes inverse tangent of 10 Rn over Rn. That is inverse tangent of 10. It is 84.2 degrees. A very large phase lag introduced by introduced by this amplifier at very low frequency, a frequency equal to 1/10 of FCL. And what happens at f is equal to 0? Of course, this is 90 degrees because it becomes infinity. So we have in the numerator we have infinity, and which is solved as 90 degrees. So at very low frequencies there will be a phase lag of 90 degrees between the input and the output. Right, what's called the output RC circuit? For output RC circuit, we have this capacitor, coupling capacitor C3, and this RC and RL are in series. So we'll apply the same analysis, and the cutoff frequency is RC plus RL, because these two resistances, they form an equivalent resistance that comes in series with this capacitor C3. So the phase lag introduced by this XC3 and this network composed of C3 and the series combination of RC and RL. This is this inverse tangent of XC3 over RC plus RL. On the same lines, we can apply the same analysis, that what happens at theta is equal to 0, and what happens when when F is very large in midband, when F is equal to FCL, and when we have F is very small compared to FCL. So you can apply the same analysis, which is left as a homework for students. Apply the same analysis that we have applied here. This one, you should apply the same analysis to the output circuit. Right, let's move on to the last part of the lecture, that is bypass RC circuit. This bypass RC circuit, as we already know, it introduces a very large resistance C2 at very low frequencies, like C2 offers, since this is inversely proportional to F, so at low frequencies it offers very large. So for frequencies that are fairly large, there is no problem, because XC2 is very small. So a very small resistance when comes in parallel with RE, it gives a very small resistance and the gain isn't affected. But what's about the FC? If we look into the circuit from here, if you look into the circuit at this point, we see, what do we see? What is the resistance that we see? We see an RE, of course, from this point to the ground, and then we have this path going back into the transistor from emitter to base, and of course there is a resistance RE, small RE, the junction resistance, and then we see an R1 to AC ground, and R2 is also AC grounded. So what should be the resistance that should come in parallel with RE? Of course, this small RE is on the output side, so we'll write it as RE. Plus we have two other resistors that are in parallel, R1 and R2, but they are on the base side. And we have already studied in the last course EDC that if we take a resistance from the output side to the input side, we multiply that by beta. But if we do the reverse operation, if we take the resistances from the input side to the output side, we'll divide those by beta. So this is R1 in parallel with R2 divided by beta, plus this resistance small RE, and this whole stuff comes in parallel with RE. This is the equivalent resistance that is seen by this capacitor C2. So this RC circuit forms this RC, this R, and this C forms a circuit, RC circuit, and the cutoff frequency introduced by this C is by this capacitor C2, that would be FCL. The cutoff frequency load is this one. So now we have expressions to compute lower cutoff frequency using input coupling capacitor, the output coupling capacitor, and the bypass capacitor. So practically we'll have three cutoff frequency values, one from C1, the other from C3, and the other from C2. So what should we take? We should take the largest one or the smallest one? Of course, we should take the largest one. The largest one. Out of these three, we should take the largest. We should assume the largest to be the actual low cutoff frequency for the amplifier. Since XC2 is approximately equal to 0 ohm at, as I've said earlier, at midband, therefore it's no problem. The gain is RC over RE. But what happens to the gain when we are working with frequencies that are very small, that are very small compared to the lower cutoff frequency? For that, this C2 isn't negligible, because we are working with small frequency, and for small frequency this X2 is large. So that X2 comes in parallel with RE, making it a larger resistance. So then we cannot neglect that. So that value is there. We cannot neglect that because this value is larger than this small RE. So the gain is effective. But in midband, there is no problem. It's superb. During midband, you don't have to make any compromise. The C2 works fine. It bypasses this RE and the gain is large. Right, we'll keep on studying, but that's all for this lecture. But in our next lecture, we'll keep on studying more about phase shifts and low frequency response of amplifiers. Thank you.